Hello. Good morning to everybody. Welcome back to our series of AI4EOSC webinars. My name is Marcin Płóciennik, and I will moderate this webinar. Today we will present a real use case exploiting the platform. We will have basically four different use cases presented, and for those that has not joined our previous webinar, we'll have also introduction to introduce a bit AI4EOSC platform. This will be a short introduction. So during the presentations, you can always ask the questions, and that will be responded after each of the presentation. And basically, I will moderate this, and I will pick up questions that you post, and the speakers will be responding. So I will also show later this QR code, so you have these opportunities. So first, we start with the introduction to AI4EOSC platform. The introduction will be done by Judith Padilla, that is researcher at the Advanced Computing and Science Group at the Spanish National Research Council. She's a mathematician with a major in computer science from the University of Cantabria and master in data science in computer science from the Universitat Internacional Mendeles Pelayo. She participates in different European funded projects, mainly within the scope of EOSC, and she finished her PhD thesis in privacy preservation techniques in data science environment. So now I give floor to Judith. So please share your slides.
Thank you very much, Marcin, for the introduction. So I hope that you all can see my slides.
Yes.
And as Marcin has mentioned, I want to briefly introduce the AI4EOSC platform. And I don't want to extend myself too long, because today is the turn for use cases for explaining us what are they, how are they exploring the AI4EOSC platform for the different AI-based applications. But I think that it's important that we introduce a little bit why the AI4EOSC platform, the different tools that we have on it, and so all of you that maybe do not know it or have never used it, then you can learn a little bit more about the platform. So let me start by explaining that the AI4EOSC platform arises as a result of the AI4EOSC project, which is still in progress, and it will finish this next month of August of 2025. And it has run from September 2022, so during 3 years. It arises an evolution of the deep hybrid data cloud platform, and we have a quite nice consortium conformed by 7 academical partners, 2 small or medium enterprises, and 1 non-profit organization. And the main objective within this project is to provide users, mainly within the European Open Science Cloud, with advanced features for performing their artificial intelligence applications, their data science applications, mainly with advanced features like the distributed learning, federated learning, machine learning operations techniques, metadata provenance, and so on and so forth, as I will explain in the following. So first, why are we interested in providing this AI4EOSC platform? So first, in order to make available to users a set of tools, a set of a catalog of also models that make them easier to develop and run their applications, their models, but also with different methods that may be a little bit difficult for them to use, such as the applications that focus on privacy, for example, with the possibility of running federated learning experiments, also making for them easier to use tools for monitoring, for using machine learning operations in production, also in order to make available for the users a set of model provenance metadata, in order to be able also to make to put the models in production, use them in production, and use the models for inference, like using different services that I will discuss in the following. But one important step that I'm sure that probably some of the use cases are going to mention is that it allows the users to have access to different computing resources in a quite simple way, in a quite transparent way, also making them available to train their models in a quite simple way, having access to those resources. So here you have the main phase of the AI4EOS platform, that is the AI4EOS dashboard, in which you can see that we have modules, we have tools, also we have a catalog of LLMs that I'm going to explain. And here you can access the different functionalities that we have within the platform. And I'm going to briefly review these functionalities because if you want to have more detail on that, we have other webinars that we held in last months in which we explore each component. But just for you to know a little bit more on all these features, first concerning data storage and ingestion, the users can benefit from a storage provider, which is Nextcloud, with 500 of gigabyte per user, but also they can import datasets coming from different openly available repositories, such as the Node, Hugging Face, etc. And this is concerning the data, but also in some cases we may need tools for example, data annotations in cases in which we are working with videos, with images, and we want to make easy for the users to make that automated labeling of the images, of the videos. And in order to do so within the platform, the CBAT and image annotation tool has been integrated for this purpose. Now we move to the model development. Within the platform, users can take a model that is already trained, but they can use it for retrain, for example, with their own data. Here I have included an example of a plant species classifier. In this case, the model, it has been already trained for being able to classify different species of plants. But if you are working in a quite similar use case and you want to make a fine tune of this model that is already training, you can take this model and fine tune it with your data, or you can just use it for inference with your new data, or you can just retrain it. And also here you have an example on how you can access to different hardware resources, the number of CPUs that you need, the number of GPUs that you may need, the model, etc. But what about the case in which a user wants to create a model from scratch? The user doesn't want to use the already trained model, but want to develop it from scratch. Then the users can access the interactive development environments that are available within the platform, from Visual Studio Code to Jupyter Lab. Here you have an example of Jupyter Lab. And here you have an example of Visual Studio Code. And here you can see again that you can configure the hardware requirements that you may need. And concerning model training, as I have already explained it, you can do it from scratch. You can take a pre-trained model, but also you can do it with PyTorch, TensorFlow, etc. But also we have different templates in the documentation, or simply guides on how you can parallelize your training using multiple GPUs and then under a distributed training paradigm. You can also perform federated learning trainings in which you can train a model without centralizing the data, having the data distributed in different machines or in different cloud providers. And we have provided 2 servers for this federated learning approach, and the participating clients can join from the AI4EOS platform for external cloud providers or from the local computer of the user. So this is other functionality that the users can access from the platform. If we go now to the part of serving the model, as I already mentioned at the beginning, we have a system for making inference of the model, which is OSCAR, that can be used to serve the models for inference, and it supports different configurations concerning serverless execution. Also, in order to build the AI workflows, we provide the users with Flowflux and Elira in order to support these workflows. And as I have already stated, in case you want to use a serverless environment for serving the model, users can use OSCAR. Also, they can do it in a dedicated server or trying the short-lived demo endpoints. So here you have the different options that you may have for inference. And now, if we have already made our model, we have served it, we can use it for inference, we have to think about monitoring the model. So concerning model monitoring, first, machine learning operations that arise as an engineer practice that can be used for streamline the machine learning lifecycle, including to track the experiments, to make the experiments, to package the experiments into different reproducible runs. And in order to do so, within the platform, we provide an instance of MLflow for being able to making this tracking. But also, we provide tools for drift detection, which is essential when we have data that are not stationary, data changes over the time, and then the concept learned by the model may change too. So in order to these drift detection methods, users can profit from this Python library developed within the project, which is called Froglos. And last but not least, we have a set of LLMs that the users can try to make common things that we usually do with chatbots, like asking about, okay, how can I use this model from the AI4EOSC platform? How can I retrain a model? Can you help me summarizing this documentation or something like that? So you have here a set of LLMs that can be deployed in the platform to be used. So here you can access the AI4EOSC dashboard in case you want to take a look to the different models, to the different tools that you can access. And finally, let me conclude in order to give the floor to the use cases, saying how is AI4EOSC empowering the scientific research. And this is our wrap up of what I have already explained, but all in all, we want to provide the users with advanced AI tools for model retraining, for federated learning, and in general, privacy-preserving machine learning, for users being able to parallelize the training in case they can access to multiple GPUs, for monitoring the models and also putting them into production with model inference techniques. And also they can benefit from these intuitive environments for developing the models like Visual Studio Code, JupyterLab, and access to the computing resources in a quite transparent way, in a quite simple way for them. And also, we allow the users to deploy their own LLMs. That is quite a new feature, but it's quite interesting for the users in order to be able to deploy their own LLMs and use it within the platform. And finally, here you have different links for the documentation if you want to learn more about it, about this. But I recommend you to see the different webinars that we have held concerning the platform and the different functionalities that you can use. And that's all from my side. And now I want to give the floor again, of course, to Marcin, but I want to thank the speakers, the different use cases that are going to explain why are they using the platform and their applications that I know that will be quite interesting. So thank you very much.
Thank you very much, Judith, for reminding and explaining the AI4EOSC platform. So basically now we will move directly to first presentation on the Thunderstorm nowcast based on pre-processed radar data. So while I would introduce Irina, you might already share your slides. So Irina Malkin-Ondik is an interdisciplinary researcher, currently a senior data scientist and artificial intelligence expert at Microstep MIS. She has research experience from the Slovak Academy of Science, Julius Maximus University in Würzburg, ETH Zurich, University of Zurich, and FIT2 in Bratislava. Currently, she participates as an investigator and work package leader in scientific projects funded by the European Horizon, ESA, and Slovak APV grant agency related to meteorological nowcasting. She also supervises bachelor and master student at various domestic international universities, such as Slovak Technical University, Comenius University, and University of Amsterdam. So, Irina, the floor is yours. You can start your presentation. Thank you.
Thank you. Can you hear me?
Yes, we can hear you very well.
Okay, wonderful. Today, I'm going to talk about thunderstorm nowcast based on preprocessed radar data, a project we have worked on within the AI4EOSC platform. First, the motivation, why are we even interested in this? Thunderstorms can cause a lot of damage. They consist mainly of high winds, which can break and damage buildings, equipment, material, plants, rip of roofs, etc. Hail, depending on the size, can cause leaf damage, reducing yield or destroying plants. It can destroy machines, cars, buildings, and endanger humans as well. And finally, flash floods, which is rapid, huge amount of rain falling down in a short time, can endanger humans, animals, can also create a lot of damage to machines and equipment, can cause the top fertile soil to go away, and it can damage the crops as well. Unfortunately, it is expected that due to the climate change, the thunderstorms will be even more extreme in the coming years. So we see that they are quite dangerous meteorological phenomena, and it would be nice to have a tool which can issue severe weather warnings for farmers and urban citizens in advance, and if possibly greatly localized. This will enable people to take preventive measures to protect property, health, and crops. This has been a problem for a long time. The traditional nowcasting methods work directly with radar data. Those are special algorithms. One is called Titan, Thunderstorm Identification, Tracking, and Nowcasting. It takes radar images, identifies storm course, and based on previous radar images, tries to predict the velocity and the direction of the storm and moves it. Another common method is called COTRAC, Continuity Tracking Radar Echoes by Correlation. It takes several previous images, tries to find a correlation, and then tries to find how was the image changed, meaning it moves all of humidity, not just the thunderstorms, but everything which was on the radar image. Both work quite well, but they have their bugs as well. Therefore, it's time to move on to deep learning techniques used in meteorology. Generally speaking, there are two kinds of interesting AI directions. One is time series prediction for following long-term patterns, and another one is image processing. In particular, we are interested in image detection, which allows one to identify and localize relevant objects. Typical architectures are convolutional neural networks. You may have met it even with your mobile phones with face recognition. Another interesting field is object tracking and recognition. It identifies objects in a sequence of images and tries to predict movements. Typical architecture is Siamese networks, and this is in particularly useful for nowcasting, and it also helps with autonomous driving as an application and similar items, or following a person in a crowd for security risks, for example. Then there are some challenges. One of the main challenges is blurry images, because unless you take very specific measures, it's usually more advantageous for the neural network to predict a huge area rather than to pay attention to details. As you can see, target image is in the left corner. Persistence, which is just movement from a time before, is in the upper right corner. And then not a very good prediction is on the first column below. This can be contradicted by using custom architectures such as GANs or DGMR, or you can use also custom loss functions, such as edge loss, to make sharper edges, to make sure that the thunderstorm in both intensity and location are predicted accurately. Another problem is that it's very difficult to predict accurately after about 30 minutes because thunderstorms quickly develop and move, and it's not reliable. A solution is blending deep learning models with long-term nowcasting models such as numerical weather predictions. And finally, we are often faced with imbalanced data sets because on the global scale, bad weather is rare, usually sunshine. For this project, we have used our own radar, which was built. It was manufactured by the commercial firm I work for, Microstep Maze. It's an X-band radar. Typical wavelength is 3.19 centimeters. The standard range is 150 kilometers. Under good circumstances, if there are mountains, this range can be somewhat slower. The scan frequency is about 5 to 5.5 minutes. In this study, we have focused only on the warm season, which means data from April to September, because in the area of the study, most thunderstorms occur within this warm season. The key radar products we will be talking about are PCAPI, which is PSEUDOCAPI 2000. PPI means we take radar data for constant elevation. For radar rotation, it's at 360 degrees. The radar spins and collects the data. CAPI means we are making a slice through several scans at a user-defined altitude. We prefer 2,000 meters. And PSEUDO means that in a long range, we do not actually see any signal at 2,000 meters, so we take something slightly up. Another product is WIL, which is vertically integrated liquid. Based on reflectivity, we can calculate the total amount of precipitation that would fall if all the liquid water in the column above a given pixel reaches the Earth's surface. So we calculate for each height, 500 meters, 1,000 meters, 1,500 meters, and so on, and sort of integrate the vapor. Now, to make our life slightly easier for this project, we convert the KP data for pixels, which is in decibels, because it's reflectivity, into warning classes, where 0 means no convective event, mild rain or no rain. 0.5 means light intensity, 1 is moderate intensity, 2 heavy intensity, and 3 is extremely dangerous, extreme intensity. Fortunately, also so far very rare. Here is a demo of a warning classes animation we are trying to develop. Gray areas means the radar does not detect any storms. Green means there is slight reflectivity, but not enough to issue warning of level 2 or even 1. Yellow is level 1. Orange is level 2, and red is a really dangerous area. Okay. We have greatly benefited from the platform during the course of the project. What we like most is ongoing support and almost instant responses to any kind of technical problems that arise. Coding was made enjoyable through the tools which Judith has presented. We like the template. Also, once the code is uploaded to the project GitHub, there is Jenkins pipelines in check. We check for code quality, help debugging, and also create automatic Docker images. Also, there are plenty of example applications available in the repository and accessible via dashboard so that we can look at how other researchers are solving their problems and maybe get some hints with the code. We can comfortably access the data through external storage. We have profited from data drift monitoring because as radar data is constantly incoming, it's nice to know when the radar stops functioning as expected, when there is a drift and the model needs to adjust. Training was easy through dashboard. we appreciated the computational resources, and we hope for easy deployment. Right now, we are testing Oscar service triggered every 5 minutes for nowcasting, as you have seen, because when we are trying to do weather predictions in real time and radar scares every 5 minutes, we need the data to be processed also every 5 minutes. Also, through this project, there was a fruitful collaboration on federated learning with Judith. And here we wrote a very nice paper about it. See the citation below. About the motivation. High resolution radar data is large and often proprietary. It's hard to centralize. Also, usually it does not come from a single radar, but rather from a radar network. Federated learning is distributed. It helps to keep private radar infrastructure without the need to exchange data on the servers. Models are trained locally and aggregated centrally, which means you need one common server to evaluate, but you don't need to share the data, which is huge amounts. And it helps to create high spatial accuracy. What we have studied is we have taken original radar images, which were 400 times 400 resolution for the build product, vertically integrated liquid. Then we downsize them to 100 times 100 resolution, which is the image, the 6 images on the left. And then because we only had one radar available, we have divided the images into 4 quadrants with the areas shown in blue on the right. We have done this for all the images in the datasets. Then a little bit about the theory, what happens next. Individual training is when we take all the data, split it into train and test, train the deep learning model, get one model which makes prediction for the whole area. Federated learning has one server, has 4 datasets. In our case, 4 datasets, 1 for each quadrant. Where the deep learning model is trained, it then communicates the weights to the server, which aggregates them and creates a model which covers all the areas based on the aggregated weights. And finally, Judith has suggested to use adaptive federated learning, which enables us to create a general federated learning model and then retrain it based on the data specifically. The reason we are doing is that due to geological factors, radar images datasets are not equally distributed. The properties of the datasets are different for each location, for each area. Therefore, the model needs to be robust and adaptable. As a new adaptive federated learning approach helps to address the main challenges that face federated learning, like poor convergence on heterogeneous data, which is the case for radar data, and it helps to generalize beyond the global distribution of data. The experiments have been carried out on the platform. They require 16 gigabytes of RAM, 10 gigabytes of disk, 8 CPU cores, 1 GPU NVIDIA Tesla T4. And now let us show you some results. The original example is high on the left, the 3 rows, the 3 columns, the highest row. And then the typical federated learning creates blur images, as you can see in the second row. And when we used adaptive federated images, we see that we have some kind of structure. Also, all of these images focus on the central overlapping part of the original image. When we stitch the 4 datasets, the 4 squares together and then cut out a centralized middle page. The images were from this wonderful website. Thank you for your attention.
Thank you very much, Nina. So let's have a look at the questions. What kind of features do you use to predict the vertical integrated liquid? That's the first question.
We use transformed radar data as such.
Yeah, in the meantime,
I mean,
I will share the link. Just a moment. I will, in the meantime, share also the link to the code. Okay, and you can think of the responses. Okay.
Okay.
Thank you.
What we do is we take the raw data from radar and pre-process it, and during the pre-processing, we calculate the products such as copy and will. And then we have a sequence of previous situations based on which we can predict what's going on. So all of the data is already pre-processed, which is time-consuming for a huge data set.
Okay, thank you for the responses. I'm sharing again the Slido. So if you have other question, you can post it now. Oh, let me have a look. So we have one more question. So what was the largest challenge in using the platform? I understand the AI4EOSC platform.
The biggest, we had two main challenges. One was using the Oscar, because we are setting it up now and we have never used Oscar interference before. So this was the challenge. And the second challenge was to understand some of the best MLOs practices, because we have used to do it a little bit different in our company, but we appreciate the simplicity, just that we had to learn a lot. We had a huge learning curve during the project.
Okay, thank you very much. Thank you again for this presentation. Okay, so now we will move to the next presentation that will be given by Mateusz Krzyżanek on integrated plant protection. So Mateusz Krzyżanek is a software developer at Poznań Supercomputing and Networking Center, and he coordinates the work of selected teams for different international projects. He's involved in AI4EOSC and also Scale AG data. He's focusing on applications that integrates data from agrometeorological stations, satellite imagery, and the pest monitoring and AI solutions. So Mateusz, the floor is yours. You can
Good morning, everyone. Thank you for the introduction. And without further ado, let's proceed with the presentation. I hope you can see my screen and everything works fine. So let's just move on. Early detection of plant diseases is critical from both an economic and environmental perspective. The sooner a disease is identified, the greater the chance to contain its spread and take effective action with minimal input. Delayed recognition often results in the need for more frequent chemical treatments, which increases production costs and puts additional pressure on the environment. Yield losses caused by diseases can reach several dozen % in extreme cases. Entire fields may become unsuitable for harvest. For crops like beet or rye, diseases such as Cercospora leaf spot or brown rust can directly affect both the quality and the quantity of the harvested product, impacting farm profitability. That's why fast and accurate diagnosis, especially when supported by AI, can be key components of modern crop protection strategies. The main idea of our use case is to assist the plant disease detection system by identifying the first stages of disease early using AI models. The results of the models are to confirm whether a particular disease is present in a given image. Specifically, the diseases in question, like I've mentioned before, are rust of rye and Cercospora beticola. These are fungal diseases that attack crops. The symptoms of mentioned diseases are visual. That is, the changes can be seen on the surface of the plant, and to be more precise, on the surface of the leaf. Sometimes, however, it is useful to take an assist with technological solutions to confirm your assessment. When encountering a potential outbreak of brown rust on rye crops or Cercospora on beet crops, an advisor or farmer can take a photo and then send it to an AI model, which will assess the likelihood that it is one or the other disease. The feedback can be valuable and be a good validation of the advisor's work. We began the process of training AI models by preparing the appropriate datasets, as the quality of the images in the training set is a very important element when producing AI models. We were anxious to meet these requirements. For this reason, we tried to diversify the types of photos we acquire, as perceived by the various entities providing them, which potentially contributes to improving the performance of the models. Thanks to the cooperation with the Institute of Plant Protection, we were able to obtain several additional sets of photos of beet and rye. The cooperation with them was fruitful, and they provided expertise in plants and diseases. We were also able to arrange trips at the time the disease occurs in the fields that we monitor. This also resulted in the acquisition of about several hundred photos of rye and beet with the symptoms of the disease. As part of their work, advisors take photos of many crops and many different fields. We were able to automate the process of acquiring photos, in particular of beet and rye, based on the ELDR and reporting of agrophages application created by Vodr and PSNC, as well as configuration with the database for storing training data sets. We designed a certain supervising system. That is, if the images are suitable, then a designated person approves them, and they go to the target database. The process was designed in such a way that the advisor's existing stationary work related to agrophage monitoring does not entail additional burden. Collecting high quality data for training AI models in agriculture is a demanding process. One of the key challenges is the seasonality of plant diseases. Many symptoms only appear during a specific growth stages or weather conditions. This limits the time window for field data collection and requires coordination with agronomists and advisors to be in the right place at the right time, basically. Additionally, some diseases are sporadic or geographically limited, which makes building a well-balanced data set even more difficult. Another layer of complexity involves the diversity of real-world conditions. Excuse me. Lighting camera types, angle of photos, and background elements vary greatly between images. And while this variability can improve model generalization, it also increases the risk of noise in the dataset. On top of the technical and logistical issues, ethical considerations are becoming increasingly important. Plant health data, especially when geolocated and tied to specific farms, can be very sensitive, which means farmers may be hesitant to share information that could reflect poorly on their practices or affect market perception. That's why transparency, data anonymization, and clear communication about how AI models are trained and used are crucial in maintaining trust with the stakeholders. Elder application and supervising. So the coordinator defines the number of monitoring points in a given province and assigns individuals responsible for monitoring specific crops. This is done on the coordinator's expert knowledge, understanding of the region, and awareness of potential threats to the crops. The assigned person is then provided with convenient tools to specify the exact location of the monitoring point. They can use public cadastral parcel databases and, for example, search for a field using a parcel number or where the observations will be conducted. So about the mobile application, the advisor makes observations in the field application. By default, he selects 3 photos and indicates which kind of frame it is. So photo of a thread in a close-up, photo of a single crop, or photo of a whole crop. When the user has the AI4EOSC tester role, his reports look a little bit different. Instead of 3 photos, he sends 6 of them, along with an indication of which photos depict the diseased plants and which one depict the healthy plants. Here you can see a couple of screenshots which show the process of adding photos in the mobile application. So first step is selecting the monitoring plant. The user starts by selecting predefined monitoring location. These points were previously configured in the system, transferred to the mobile application via API integration. The user sees a list of locations with crop and season details. Next step is starting a new report. So once a point is selected, the user initiates a new report by tapping the plus button. That starts the process of documenting a potential threat. Another step is filling in the disease details. The user then selects the disease observed in the field, for example, Cercospora leaf spot, specifies the BBCH growth stage, and enters the percentage of the affected leaf area. This provides contextual information necessary for proper diagnosis and documentation. The fourth step is adding and categorizing photos. So the user adds up to 6 photos and directly from the device. Each each photo must be categorized, like I mentioned already before. For example, indicating whether it shows a disease area or a healthy part of the plant, so that this information is tied to the image itself. There's also space for comments, such as such as specific visual observations or field conditions. Fifth steps would be finalizing and sending the report. After all the information is filled in, the user can optionally indicate if a chemical treatment is required and add further notes. The report is sent to the server by pressing send, obviously, where it becomes a part of a central data set. It also remains accessible in the mobile application for later reference. So like it stays in the application, but it also goes to the data set, to the database. The last step would be synchronization and storage. The submitted report, well, actually I've already said that, but it's synchronized with the database. After such a report is entered, it goes to the supervisor module, where the person responsible accepts or corrects the report and then sends it to EBIS. What is EBIS? I will explain in the next part. Since 2021, we have collected over 200,000 reports, most of which include multiple photos. This provides a powerful data set for training AI models and plant disease detection and crop condition assessment. EBIS. So to store the collected images, we use EBIS software developed by one of the teams from PCNC. It allows catalogs to be described using attributes and offers the ability to quickly search the database using filters. So it was a really helpful tool because it allowed us to keep most of the things in one place. Later on, we even expanded EBIS's part in our system, but I will elaborate on this subject later in the presentation. Trained AI models are also stored on EBIS with a public link exposed so that they can be accessed on the AI4EOSC marketplace. On the right side, you can see an example of a file that's being used to describe the particular data set with the attributes. Yeah, like I've said, it's available on the marketplace. It's called Integrated Plant Protection. So anyone interested can go directly over there. AI models training. So current recognition methods use deep learning models. We focused on creating a solution resistant to hallucination. Therefore, we decided to build a deep learning system composed of two convolutional neural networks, network models. So CNNs are a type of artificial intelligence model designed to see kind of and understand image, much like the human visual system. You can think of them as a system of layered filters that gradually learn to detect increasingly complex features in a picture. At the beginning, the model looks at very basic patterns like edges, lines, or simple shapes. As the image passes through deeper layers, the network starts recognizing more detailed elements, such as parts of a leaf, disease spots, or texture changes. Eventually, the network can associate these features with specific conditions, like a healthy plant or a fungal infection. The power of CNNs lies in their ability to automatically learn what to look for, without us explicitly telling them which features matter. Instead of hard-coding rules like brown spots mean cercospora, We show the network enough examples, and it figures that out on its own. This makes CNNs ideal for problems where visual patterns are complex or subtle, like identifying early stages of plant disease. Task of the first model is segmentation. We implemented the unit architecture model. We use the obtained model to extract the main area, indicating the leaves class, because the leaves clearly inform classifier about the health of plants. So we ensured that the background artifacts, soil, weeds, will not affect the next model's predictions, which will be focused on the disease occurrence. And this is exactly what you can see on this little example here, where only the leaf is the leaf part is left. The second task is classification. We implemented the CNN model for binary classification. Input to models are 512 by 512 RGB images. During training, we used the data augmentation and undersampling. PyTorch was used to build the system, implement, and train models. The data set used for the training is available on Zenodo, so anyone interested can also get their hands on it. The repository contains high resolution RGB images captured by field advisors and selected by experts for the dataset specifically designed for training to models to recognize Cercospora leaf spot disease in beet and brown rust of rye in rye. The dataset consists of 397 images and includes original photos along with the binary masks for two categories, leaf segmentation and disease spot segmentation. As the trained AI models are intended to support the work of advisor or farmer, we decided to add the possibility of using such models through the mobile application. First for advisors, then in the next stage for farmers. EBIS as an enhancement, EBIS enhancement as a processing tool. So, in addition to being a classic database, EBIS also offers processing capabilities. We were able to configure EBIS so that it was connected to Edwin's system, and that allows us the configuration with the mobile application. This has enabled automation with the mobile app in the sense that when a user creates a threat report and it relates to one of the two plant disease cases that are covered by our models, the attached images are sent to EBIS, which does the data processing and then sends the model result to the mobile application. Thus, the user will notice the entered information with the result in the report they submitted. The result will be added with some delay due to processing time. And this simple diagram below here shows what I've basically explained, like the whole data flow. Mobile application, the testing phase. So we call it the pre-production phase, is the stage in which the developed AI models have been integrated into the application. It's already familiar to you. I mean the one where you can make a threat report. The application is used daily by agricultural advisors for field monitoring. And in this phase, advisors continue to carry out their regular field observations, but now they additionally receive AI-generated information on models that assess potential threats directly from the uploaded photos. In In the new version of the application, when adding information about the object in the photo, the system evaluates whether the object may represent the disease or not. Additionally, the report is now clear. The report list now clearly indicates whether a given report contains insight derived from the AI engine or not. This setup allows advisors to evaluate the model's performance in real-world conditions and determine whether it is useful in their daily work. The ultimate goal is not only to support advisors in their monitoring tasks, but also perhaps more importantly, to assist farmers who inspect their own fields, but may not possess the same level of expertise as a professional advisors from agricultural advisory centers. Thank you for your attention. If you have any questions, or if you're interested in getting more detailed information, for example, regarding the model, training process, all the numbers, feel free to ask or contact me on this email address. Adam Foyot is also a person who's responsible for the tasks performed by Vodr, and Jędrzej Smok is a main AI model developer who was behind the whole developing part. So once again, thank you.
Thank you, Mateusz, very much for your presentation. I have to say also, Adam is today with us, and as you mentioned, he's from Agricultural Advisory Center in Wielkopolska. So he develops web-based solution system for agriculture and API integrations, and basically he also contributes to different projects, international, but also the Polish Edwin platform. And basically he's also working on this agrometeorological station, satellite imagery, agrofag monitoring. And basically I understand that you both, since you are connected, you might respond to the questions. So let me first share again the QR code, and okay, I already see a lot of questions coming, and those questions are actually first to you, and then there was several questions also to basically that I think Judith will take over because they are more general and more to the first presentation. So and also there was one to the second presentation. Okay, so first. So the mobile app is already available. If everybody can try, I think you partially responded to the question, but maybe can you address that?
Yes, so of course, like I've mentioned, right now we're in the pre-production testing phase. So a selected number of advisors has access to this new feature. And once they confirm that the results are satisfactory in their mind as an experts in the fields, then we will allow farmers and basically all the users have the new features.
Okay, thank you. So the second question, are you planning to address also other diseases?
Well, because we have already the whole mechanism, we want to promote it and work with other diseases and models. We have collected over 200,000 reports. They contain multiple photos. So this forms a rich data set that can be used not only to train AI models for the currently monitored diseases, but perhaps also develop models for other plant diseases and pests. Our monitoring system covers a wide range of crop diseases and harmful organisms. We focus only on a small part of it, so there's definitely a place to expand.
Okay, thank you. So there's the next question, but since I saw the already response to it, so I will skip part of the question. So there was a question, but you already responded on how you obtained the database. So you already explained that, and on number of images you already explained. So there's another question question. You have a data set per plant spices, or you need to classify also the plant spices?
I'm not
And
sure
I think
if
you also I think you also responded to that you don't recognize what is the plant, but you already have prepared
yes,
those sets. Yeah. So
exactly how
I
you
believe I understand from this. So there is another question. Have you tried to use drift detection for the problem or diseases stationary?
Regarding the technical parts of the whole AI model training, I feel like that's a very good question, maybe to Jędrzej, who should be somewhere in the chat looking at the stream. But we have prepared a very detailed PDF documentation file about the models. So anyone interested in that, we can provide it. That's no problem.
Okay, so if I can add just to this, respond to this question, as I'm also somehow involved, I don't think this drift detection is at the moment used at this is stationary. So that's what I know. But okay, so Mateusz, thank you again. I think we don't have more questions to you, and
Thank
I
you
would
very
like
much.
to ask Judith again so you can show up. And there is a question if the AI4EOSC services access be offered to specific use case only, or it can be offered eventually for projects access via EOSC EU node as well. Can you reply to that?
Yeah, for sure. Currently, we are giving access to the platform to the use cases that are internally to the project, that are the three first use cases that have already presented today, and Helena, that is part of the third use case. But also we have some open calls for external users. And for example, the last use case that will be presented by Maria is part of one of the use cases that has been supported within this external call. However, first, we have different authentication levels for using the platform. So with the basic authentications, the users may be able to try a model that is available in the platform, to train the model in their own cloud resources. That's with the basic one. And with the, let's say, full authentication level, then the users can access all the functionalities of the platform. And for having that level, currently the AI4EOSC use cases, also the iMagine use cases that are using the AI4EOSC software stack too. And also we have recently involved use cases and the models that they have been creating from the AI4Life project. So in case you are interested in using it, we always tell you that you can be aware of the open calls for external use cases, but also if you send us an email, we can to the project management, we can always try to see ways for collaboration, as we have already done with these other projects such as AI4Life. Yeah.
Thank you for this answer. We have two more questions to you. One is more request. If you can, in a moment, share again link to the paper of federated learning or the title.
I think that it was already Irina saw it, but if you let me search it, I can.
Yeah. Okay. So or Irina, if you can, in the meantime, share again this one slide. But in a moment, I will stop my sharing. But let me give one more question first to Judith. Does AI4EOSC have globally adopted metadata or ontologies in use for AI machine learning, like Croissant? Sorry, it went somewhere up. Like Croissant for dataset or FAIR for LML for models?
Sorry, I was muted. Even I'm not part of the development of this metadata part. We are working on develop these metadata ontologies for the models of the platform. I think that maybe in the documentation you can find more details about the current methodology that has been used. And concerning, if you let me share my screen quite quickly, concerning the first question that you asked, the second question that you asked me concerning that paper, I have just find it just in case. Yeah, here it is if someone wants to take the title or to search it.
Okay.
Okay, thank you very much.
Thank you very much for that. And basically, we are moving now to next presentation from object detection to semantic segmentation by Elena Vollmer from KIT. So, Elena, if you can share your screen while I will introduce you.
Sure.
Elena Vollmer holds a Master of Science degree in mechanical engineering from the Karlsruhe Institute of Technology in Germany, where she is currently a PhD student and research associate at the Institute for Industrial Production. Her research revolves around conventional and AI-based image anomaly detection methods, specifically to aid in the monitoring of energy-related systems. Her expertise extends to multispectral and thermographic data, unmanned aircraft system technology, and geographic information systems. So, Elena, again, the floor is yours, and you can start.
Thank you. Yeah, I hope you can see my screen. Exactly.
Yes.
So yeah, my name is Jelena Vollmer, and I'm gonna be discussing how I use the platform for this third use case. As mentioned, I'm a researcher, so I have more of a theoretical approach, but my data surrounds thermal imagery and all manner of image analysis tasks. So maybe to start off, I'll be delving into motivation-wise first thermography for all of those of you who aren't familiar with what it is, and especially its usage in the energy context and how I use AI to this end. So I'll be introducing the 3 deep learning models that I've integrated with the platform, and then exactly how you can use the platform. And I decided to present this more in a way that resembled Judith's presentation from the beginning. So trying to show how I use the platform, but also how you who are watching might be interested in using it as well. So starting off with the motivation, this is really centered around our urban environments. So more than half of the world's population live in urban areas and cities, and these consume the vast majority of our energy. And heating actually accounts for half of the global energy use of buildings. And so its supply is also an essential service. Now, given the ongoing energy crisis, especially here in Europe, it's really important to maintain a high efficiency and minimal losses in all the involved infrastructure surrounding heating. And so I asked myself, how can we combine different technologies, including AI, to support with this heat-related urban infrastructure maintenance problem? And so we can use thermography, as visualized here on the left side with an AI-generated image, which is basically all objects that have a temperature greater than 0 degrees Kelvin emit radiation that depends on their temperature. And so using thermography, we can measure this infrared radiation, so the heat of the given surroundings, and generate this kind of heat map. And if we combine this with unmanned aerial vehicles, so colloquially said drones, we can inspect infrastructure and pinpoint areas of unwanted heat loss that would otherwise be invisible to the human eye. So how can we implement this? Well, we have some kind of urban infrastructure that might be damaged. We organize these abbreviated UAV flights to acquire all manner of imagery. So this includes our standard red, green, blue, as we call it, imagery that your standard phones can capture as well, and also our thermal imagery. As you can see, the bottom 2 images in grayscale format. So the brighter pixels are the higher temperatures, and the darker ones are the lower temperatures. And if we analyze these, we can identify thermal anomalies which we can then use to identify areas that require repair. And so this last aspect is really where the focus of AI or AI models can help with this, with automating this analysis. Exactly. So the deep learning models I've developed, or I've integrated into the platform, I should say, center around two different infrastructure and aspects. So the first is the use of energy, so the buildings themselves. And so here this model is called thermal bridges on building rooftops detection. So it's about identifying different inconsistencies, issues in building rooftops where heat leaves the building and is not accounted for, and we can help support energy retrofitting measures in this instance. And the other two models are centered around the supply of energy, specifically via district heating systems. Now, for those of you who aren't aware, district heating systems are networks of underground pipelines that supply heat to buildings, for instance. So hot water is transported through these underground pipelines, and when a leak occurs, it means this hot water flows into the surroundings, and we have an anomaly in our thermal images, a hotspot that doesn't belong to any other aspects of our urban environment. And so this combination of the two models, the first one identifies all manner of anomalies around our district heating system, and the second is really about sorting out false alarms, because we have lots of warm things in our urban environment, like people, manholes, buildings, cars, that aren't leaks. And so the idea is to identify the leaks as the remaining anomalies. Now, in terms of AI, these problems are twofold. The first is really a single class object detection problem. So drawing these bounding boxes around the anomalies that are thermal bridges in this instance, or also can be identified as an instance segmentation problem, which is a pixel-wise definition or classification. And regarding the other problems, so our two models, these are semantic segmentation models. So we just have a pixel-wise classification. The first is binary, so anomaly or background. And you can see here all the areas are masked out that aren't close to the district heating system. So this is some data pre-processing that the images undergo. And the second or third model, I should say, is a multi-class semantic segmentation problem. As you can see with the legend, lots of different classes, such as cars, street lamps, manholes, that pertain to our standard urban features. And we want to identify at a pixel level to compare to the results of our first model. Now, this data is acquired, as mentioned, via unmanned aerial vehicle with different conditions. So you can see that there's always this dual camera that acquires both the standard red, green, blue, and also thermal imagery. And the images are acquired in Germany for the first case only in Karlsruhe, and the second in Munich as well as Karlsruhe. Now, regarding the models themselves, some information. So as I mentioned, I'm a scientific researcher, so the focus really lies on creating also publications and comparing things and finding the best methods or best models. In some instances, you can read up on the different models themselves in these publications. This one model the publication is under review, so that's not yet published. But in essence, the first model, developed initially by colleagues of mine, compares different object detection, also instance segmentation models, uses detection and PyTorch, whereas my two models, semantic segmentation ones, the thermal anomaly segmentation uses segformer models, as well as classical CNNs, and PyTorch based as well. While the thermal urban feature segmentation was more a comparison of different data preprocessing methods, so that focuses only on the UNet CNN using TensorFlow. And I also implemented some energy monitoring to identify how much energy the training consumes. Okay, but coming to just a quick visualization of each of the models, I don't want to go too much in depth here because I'm sure what you're interested in is in the platform and how to use it. So just a brief overview, I thought this was the best way to visualize it. For the first model, we have the RGB images combined pre-processed with thermal ones, as well as a generated heat map that create our input data. And so we then can get these predictions from it. And here's just a brief video that combines these predictions made by the best performing model, the Mask RCN N-Swin transformer. And so you can see how it identifies the different bridges on the building rooftops. There we go. For the thermal anomaly segmentation, we use, as I already mentioned, these masked thermal images, as well as the additional unmasked for giving some global context to the model. And so we get these segmentation masks as outputs. And here, as an example, flyover video as well, showing how the model identifies and predicts where these areas of interest, these anomalies lie. And the thermal urban feature segmentation uses a combination of RGB and thermal imagery as input, exemplified here what the outputs look like. And then again, we have this example flyover, and you can see it classifies the manholes, the cars, buildings, and so on. Okay, coming to the platform itself. So first of all of these models are implemented as modules on the platform. So this means the models themselves, the code to train them and infer with them, as well as the API to connect it to the platform. So you can find them here. As mentioned, the thermal bridges on building rooftops detection, the thermal anomaly segmentation, and the thermal urban feature segmentation models. And obviously the important aspects here are, as I mentioned, training and inference. And so just to walk you through the different things you can do or that are also implemented here with these different models, starting off with training. So first off, as was already mentioned, a really cool aspect of the platform is that we have these resources that are available to us. So you can see quite a number of GPUs, which obviously for training larger AI models is very useful. But then we can also train these models themselves directly. As exemplified here, we can create a deployment of each of these, and you can see in the Docker options, it takes the image that is already built for this specific module or a model, in this case, the thermal urban feature segmenter. So all the code, everything relevant is already in there. And we get all the resources that we need. And another cool aspect is that we can use the external data storage. So Nextcloud, as already mentioned by Judith, and for all the, or for two of the models, I've published the datasets necessary for training on Zenodo as well. And as you can see here, when you create such a deployment, you can include these datasets, and then you have them available to you directly for training. The third one will be published as well once the publication hopefully is through. So here you can select these, and then they're added to the deployment. And just basically to show you, I don't have a specific UI built on top like the previous use case showed, but it's still possible to train the different models. You have lots of different parameters you can define. So you can use different backbones, different pre-trained weights, and different, for instance, processing methods for this model. But something I'd like to highlight here as a researcher especially, you can use MLflow to do your experiment tracking, which you can also access via the dashboard. And this is really very neat. I've exemplified it here for the thermal anomaly segmenter model, which has implemented multiple training phases. And so I can group the different trainings and see, okay, for this group, I still have all my training phases together, and I can compare these. But I can have a look at each of the different outputs, not just the different keywords and so on associated, but obviously the metrics. And these can also be displayed nicely in a graphical format. And so you can really track how your models are being, like the outputs of the training and which are best and so on. Another brief thing I just wanted to mention is federated learning. Use case 1 obviously went into a lot more detail on this. But some people from the SEC, so the KIT, my university, and the IISAS from Bratislava also have been working on implementing NV-Flare for the platform and enabling it for the thermal urban feature segmentation module, which isn't yet complete, but I've just included this reference at the bottom. There's some publications on the way regarding that as well. So for this instance, for instance, you would have the 2 different cities, Karlsruhe and Munich, that have separate data and don't want to share them, and so can represent 2 different clients that train a model together without, as mentioned, sharing any of this data. Coming to inference, obviously just showing the Swagger user interface again, you can also predict with the modules that are provided. So all of these modules on the marketplace have included a pre-trained model. And so you just need to input a file that has been preprocessed in a similar way, such as those that are provided in Zenodo, and you can use the model to predict on these images. But the platform offers nicer interfaces than this to work with the models. So first off, just as a basic, a thing that lots of users can use is these try me deployments. So when you can request it here for each of the modules, and you then get this sort of nicer visual user interface where you can just drag and drop a file and the model outputs the prediction results. And here, as you can see, it's not just the segmentation mask that I've outputted. This is how I formatted it. So you can see, okay, given these different inputs, as I mentioned, different pre-processing variants, different filters I've applied or that are applied automatically, gives us this segmentation output. But for these are only, as you can see, temporary deployments deleted after 10 minutes. So for proper user interfaces and using the models for inference, OSCAR is really the way to go, which was already described in the last webinar in great detail. So I'm just going to briefly show how I use it here, and also mentioned by Irina, of course. So you can create these services in OSCAR as exemplified here, the thermal bridges on rooftops detector. And as you can see exemplified here, the cool thing is that you can create, this is for privacy reasons as well, you can create a general service as well as you'll have your private service to use. So the bottom one has my specific ID, and you can use either. For the first exemplified, you can drag and drop your file. Again, you can see in the logs that the inference has been completed, and you can get these outputs in the output folder. So this is public. Everyone can see these outputs and also the input data you've added. But if you have, for instance, with this example, a building owner who's acquired some images of his own building and doesn't want to share these with everyone, you can use your private bucket and input the image here, and then get this specific output just with this. So for your private, and you're the only one that sees this output in the end. So just to exemplify here, you have the public version and your private one as mentioned. So this is very helpful for different services if you have privacy issues in mind, similar to federated learning, of course. Yeah, so this is a summary of how I use the platform for different aspects, obviously very research focused, but I hope that you were able to take some insights away from this and maybe use it for your own means as well. Thank you very much for your attention.
Thank you very much, Elena, for the presentation. And let me share again the QR code so people could ask the questions. And in the meantime, there's a first question to you. Let me have a look where it is. Have you used the CVAT method for annotating the images?
No, unfortunately, I haven't. That tool was included after I'd already annotated my data, so I didn't. But it's really cool that they've included that as a service, so I would definitely give it a shot if you haven't annotated your data yet.
Okay, so I'm looking if there are any other questions to you. I don't see for the moment. So there is, okay, so we don't, so thank you again. I don't see more questions. Yeah, have you used external data sources? There's another question.
External data sources, what is specific? I mean, I use pre-trained weights for all my models for training. So since this is a specific image analysis problem, I use either like semantic segmentation, pre-trained weights, so larger data sets, just RGB based, so using standard imagery, and then in the training process, the model is adapted to this thermal or multispectral problem, if that helps.
So if I follow up, the author asked, additional to this, yes, so that he means the other, the images from other countries that may be open available.
Yeah, unfortunately, there aren't a lot of or any images available of this data type. So these combined RGB or thermal or just thermal data sets for these UAV-based problems available online. That's why I'm also, I think it's really important to include these data sets on Zenodo and make them public so that other people can then access and use my data sets as well.
Okay, thank you. So thank you again, Nina, for your presentation and the responses. And now I move back to Judith. I will stop sharing. Judith, there is still a coming question to you on basically the regarding the model and data and dataset metadata. And if what kind of standards we are using, yes, if you can say a few words.
Yeah, I just wanted to show this GitHub repository because I thought that it was publicly displayed in the documentation, but in this repo, you can see the tools that are used for this metadata to describe the data, the models, and so on and so forth in order to describe the models that are on the marketplace. I wanted to show the application in which we can see like the ontologies and the connections between the different components, but I have noticed that it's not publicly available yet, so I'm not sure if I can display it, but just in case, for the metadata descriptions, we have used this own made AI4 metadata repository. So here you can check the details containing the metadata validation and so on and so forth. And this is also available in Zenodo, so in case you want to check it.
Judith, thank you again. And I think we would basically move to the last presentation from today. So that is on satellite data integration with AI for high quality multispectral imaging. So this will be given by Maria Peña Fernandez. So please share your slides. In the meantime, I will introduce yourself. I will introduce you. So Maria Peña Fernandez is a researcher at the Advanced Computing and the Science Group at the Spanish National Research Council. She's a mathematician and a physicist from the University of Cantabria. And she has master in data science from the same university. She's working on her PhD thesis in biological variable artificial neural networks. So Maria, the floor is yours. We cannot see, I think, you now yet. Let me check. Have you also start the camera?
Yeah.
Okay, so please, the floor is yours.
Okay, thanks. I hope you can hear me right.
Yes, now, yes.
Okay. Thanks for inviting me to this webinar. I'm just going to explain an external use case of the platform, which is about satellite images. And in particular, in this presentation, I will go through the whole workflow that allows us to obtain new products with high spatial and spectral resolution. So to set the scene, remote sensing is the process of detecting and monitoring the physical characteristics of an area, and it is done by measuring the emitted or reflected radiation. The data acquisition is provided by sensors that are usually placed on planes or satellites. We have Copernicus, which is the Earth observation component of the European Union's space program, and it is the world's largest provider of this type of data. It collects information from different missions, and in this work we have centered our attention in both Sentinel-2 and Sentinel-3. In the case of the Sentinel-2 products, just to mention that they have 13 spectral bands and a spatial resolution of 10, 20, or 60 meters GSD, depending on the band. We have just focused on those that have a 10-meter GSD of spatial resolution, which are 4 out of the 13 spectral bands that each product has. And we also have used the Sentinel-3 products, which have a higher spectral resolution. Each product has 21 spectral bands and a lower spatial resolution than the Sentinel-2 mission, which had 300-meter GSD. The objective, therefore, was to obtain new products by combining the information of both missions so that they all have 21 spectral bands and a spatial resolution of 10-meter GSD. Therefore, what we wanted to do was to improve the spatial resolution in a factor of 30. Okay, to do so, we used a generative adversarial network, and as you may know, it is a combination of 2 different neural networks. We have used as generator an architecture that we have found in a paper in 2018 by Lanaras et al. And it was composed of 32 residual blocks and 256 neurons per convolutional layer. And as loss function, it was used mean absolute error. A scheme from this architecture can be seen in part A of the image depicted on the slide. And as you can see, the inputs are the images from both missions and the output are the super result products. On the other hand, we have the discriminator, which is also based on a paper written in 2016 by Radford et al. And it has 2 convolutional layers. And the loss function that is used here is the binary cross entropy, because we are working on a classification task between super resolved images or high resolution ones. Okay, we compared the performance of this network with some other algorithms. We compared it with the CNN, that is basically the generator of the CAN. And as we can train it separately from the discriminator, it will allow us to see the difference between using the discriminator and don't do it. We have also used a bicubic interpolation, which allows us to obtain the values inside an area of interest, like the one depicted on the slide. And it is done by using the known values of 16 neighbor pixels, as you can see there. And finally, we also use a pan-sharpening technique, which is commonly used in this type of tasks. And it improves the spatial resolution of low-resolution satellite images by taking as a reference one of the high-resolution product, which is a panchromatic pan. And just to mention that it uses the intensity hue saturation Gaussian method with the Mayat algorithm that just uses wavelet transforms. And just moving to the workflow itself, the first process that we have to do was to collect the data, and it was done by using the Copernicus browser API. And we try to take images from both missions that have to be compatible. And we did under certain conditions. First, a climatic one. We didn't want clouds in our images. Also, a temporal condition. We wanted them to be separated at maximum 1 day apart. And also a spatial condition, which is that we obviously want them to be from the same region. As you may see from the slide, we have taken different regions from different terrains. We have cities, we have deserts, also some coast zones, some snowy regions, and finally some forests, so that we can make our models more robust, and then we can predict whichever terrain we want in the future. So once we have collected those data, we have to prepare them to work with them. So we went under acceleration process. The first step we did was to change the format that these products have to GeoTIFF, which is a much more usable format and easy to work with Python, and also with some other programs that we have used to check the images. Then we homogenize the coordinate system of both images, and then we intersect the coordinates, taking a special care of those nouns that could appear somewhere and that would have some problems in the future. And then we cut the Sentinel-3 products. As you can see from the image above, there's an original Sentinel-3 image, and once it has been cut by taking into consideration the coordinates of the Sentinel-2 one. Therefore, you can see how much difference in size can be seen from both missions. We then resize the pixels of that cut so that we could ensure that the ratio 130 in the size of the pixels was maintained. And finally, we intersected again the coordinates and cut both the images from both missions. And in the part of the slide below, you can see an example of those cuts once all the process has been carried out. And you can see also the difference in the resolution. Okay, so finally, we did the creation of the datasets itself. And as you may know, these networks are among the supervised learning algorithms, which means that they need targets to learn. And to do so, we based on the idea that the detailed transfer from high resolution to low resolution bands is a scale invariant, which means that we could train the mapping from 9 kilometers to 300 meters in spatial resolution to predict the 300 meter to 10 meter. We used 35 pairs of normalized images to train, 5 to validate, and 5 to test, whose resolution has been reduced. And just to mention that the test images that we have used are introduced finally into the networks, both at lower scale and also at the original one, so that we can analyze both results and see the differences between them. And in the slide, you can see some inputs to the image, to the network, sorry, the Sentinel-2 300 meter, once it has been downscaled, also the input from Sentinel-3 at 9 kilometers, and also the target, which corresponds to the original Sentinel-3 image at 300 meters. Okay, so here we have some results that we have obtained once we have introduced the test images into the networks and the other algorithms at lower scale. And we can do a quantitative evaluation because, as I mentioned before, we had the targets. We use 4 different metrics that take into consideration different aspects of the image. We have used the mean absolute error, the relative absolute error, the signal to reconstruction error ratio, and also the spectral angle marker. In the table, you can see the different results that have been obtained for the test dataset, and you can see that the performance of the networks is much better than the ones of the traditional algorithm. Here we have the global analysis, but we have also made some one-to-one analysis, and these results are also seen there. In fact, we also saw that the GAN is the one that obtains the best results, and it particularly improves by about 30% the MyRI and SVM over the traditional ones. We also did a qualitative evaluation, and in the image, you can see in columns different combinations of the bands of a Sentinel-3 image. And in fact, the first one corresponds to the combination of blue, green, and red bands. In rows, you can see the input, the target, and all the different predictions from the different algorithms that has been used. And as you may see, the neural networks outputs are much better than the one of the traditional algorithms. And if you see the second and third column particularly, you can see how better the GAN is with respect to the CNN in the color compositions that appears there. And in the case of the traditional methods, just to mention that they have just blurred the input from Sentinel-3. And in the case of the pan-sharpening technique, it also adds some noise that makes no sense here. Okay, at original scale, we could only do a qualitative evaluation, but not a quantitative one because we didn't have the targets. So in the image, you can see the same configuration as we had before, and we can clearly conclude that the traditional algorithms are not functional for this task of super resolving images by a factor of 30. And in the case of the networks, we see again that the GAN seems to perform better with a higher contrast in details, and also seem to be in color composition much more faithful to what it can be intuited from the input. So going to the AI4EOSC platform resources itself, we have created a deployment. Well, I'm part of a team of 3 people, and each of us have created our own deployment, and we are working on our own, but we have linked our Nextcloud accounts, and we have there a shared folder, which is very useful for us so that we can work on our own, but we can see which other advances have been carried out. So yeah, I have here a screenshot of my dashboard and also what can be seen once I access to my deployment. I will try to show you directly on the internet. Okay, so here's my dashboard, and once we enter, okay, well, maybe it's a bit slow, but I have already here. Okay, so here I have some of the notebooks that have been used to produce the results and everything that you have seen. Here, for example, the one about analyzing the results with the different images that I have already showed you. Also, the one that produces the super resolving images, and the ones that have allowed us to train. There's a lot of warnings because of the TensorFlow package, but it is working, as you can see. There, the box, yeah, everything. So we are now working on including some atmospheric corrections to the images once they have been collected and before introducing them into the networks. And we have found some difficulties as the results that we are obtaining are not the ones that we expected to get. So we are also monitoring the training by using TensorBoard, and there we can monitor whichever feature we want from the training. And in particular, in this screenshot, I can show you the maximum value of each band of a particular image and how it evolves with the different epochs. So finally, to sum up, as I have mentioned, we have obtained new products with those 21 spectral bands and 10 meter GSD of spatial resolution with faithful radiometric information. And in particular, the GAN is the one that outperforms the rest of the algorithms, and it is followed by the CNN. So we have checked that the idea of the detailed transfer scale invariant is correct. And on the other hand, we have also checked that the traditional algorithms, both pan-sharpening and bicubic interpolation, do not work properly for this objective. As I have said now, we are now working on atmospheric correction, so there's a lot of work still going on with this task. And finally, the fact that this AI4EOSC platform has allowed us to both develop the code and also train the models as you have seen. So yeah. That's all.
Maria, thank you very much for your presentation. It was very interesting. And now I will share at the last time the QR code with for the questions, but we already have several questions. So first of all, first question, quite interesting application. Is there any paper with methodology applied that can be checked, or a repository with the code?
I don't think that the repository is still open. I'm not sure, but we are trying to publish a paper, but it is still not in any
It's not yet ready.
anywhere.
Okay. Okay. Thank you very much. The next question: are those Jupyter notebook available openly?
No,
Okay.
it's not open the repository yet.
Okay. Next question. How have you deal with the data storage? I assume that you have hundreds of gigabytes of images.
Yeah, I forgot to mention that. As we have this Nextcloud account with a lot of space, we can save it there. So it is essential for us to have this Nextcloud because otherwise we couldn't store this information locally.
Okay, thank you. And I think that's that are all the questions. So thank you again. I am stopped sharing, and I would like to thank you again, all the speakers. Thank you also to all that joined our webinar. And yes, so that's it for today. And have a nice day. Have a nice weekend. Bye-bye.